Hello, everyone. My name is Pierre BREQUIGNY. I'm assistant professor at University of Orléans, and it is my honor today to present this work at the European Biomass Conference about ammonia and syngas combustion in a spark ignition engine. This work was financed by the CNRS FIT Federation. To start with, I'd like to time travel with you, more particularly in Belgium during World War II, where due to diesel shortage, the Belgian people converted their buses fleet into coal gas ammonia operation, as you can see from this image. So there's two things to notice here. First, it is the first dual fuel engine ever reported. And second, it was operated on coal gas, so syngas and ammonia, which is our concern today with this presentation. And we will see how it is coming back into fashion 80 years later. So let's go back to the present, or maybe to the future. Well, you are all aware about the current context of limiting our temperature increase below 1.5 degrees in the next years and reducing the CO2 emission for Europe by 80 to 95% compared to 1990. The consequences are the following. We will have an increased demand for alternative and renewable energy sources. And as you can see from the 2050 roadmap of the European Climate Foundation, we could see a potential increase of the biomass share in the energy mix, and this might be pushed more due to the recent event in Europe. Well, to get energy or store energy from biomass, one way to do is the gasification, and it is interesting mostly if the feedstock are wastes, such as agricultural ones or from sewage sludge. And in those cases, it is better than landfilling in terms of life cycle analysis, can also avoid some soil contamination, and it is even better with a local use to limit the transportation. The problem with gasification is that it can lead to impurities, so ashes, tar, char, and sometimes ammonia. And this is especially true when the feedstock is nitrogenous rich, as it is with manure or sewage sludge. And most of the time, this undesired ammonia is removed before a combustion application, such as an engine for CHP, but with a supplementary cost. As you can see from this table showing different references, the ammonia content in the syngas can depend on the feedstock itself or on the gasification process as well. The question is, how this varying quantity of ammonia in the syngas can impact the combustion and the performance of an engine in a jet set application, for example. To extend a bit the context, recently ammonia has a renewed interest to be used as a fuel because it is a promising energy and hydrogen carrier. It is a globally traded carbon-free chemical, molecule itself is carbon-free, and it is relatively energy dense, as you can see from this bar chart, compared to liquid hydrogen, for example. However, its combustion remains very challenging, especially looking at these properties in comparison to gasoline. So its auto-ignition is very difficult, and its combustion is very slow, as you can see here. So one way to use ammonia as a fuel is to blend it with another fuel, for example, hydrogen or methane, which are well covered by the literature currently, or ethanol, for example, in order to limit the carbon footprint again, or eventually syngas, and we go back to the Belgian bus in 1943. Therefore, our objective with this study is to assess the impact of ammonia on syngas combustion in a spark ignition engine that you can see here on the image in terms of performances and emissions, and see if we can consider ammonia as an impurity or as a potential co-fuel, and see if it can be an asset or at least not a drawback. To fulfill this objective, I will start with the experimental setup and conditions we studied. I will show then the main result comparing syngas to methane first, used as a reference fuel here, and then see the effect of adding ammonia in the syngas. So let's start with the experimental setup. We used a research single cylinder engine test bench whose characteristics are shown in the table here. Its compression ratio is 11.7. The selected syngas composition was taken from the work of Sewage and co-workers, which is assumed to be representative of sewage sludge gasification. And to reproduce it, we use several gas bottles connected to a gaseous flow meters and a gaseous injection rail to inject the blend into the engine through an intake plenum to ensure full premixing. The conditions were the following. We fixed the engine speed at 1,400 RPM with an intake temperature of 30 degrees. We choose an optimized spark timing in order to get the best work for the engine. And first, we compare the pure syngas with methane from lean to rich mixtures, and then studying the effect of adding ammonia into the syngas using different percentage of ammonia into the fuel. So we now come to the results. I will start with the performances comparing the pure syngas to methane. And I will show you the indicated mean effective pressure, IMEP, showed with the field symbol here on this figure. It is basically the work we get on the piston. First, we can say that we get similar result to the previous study of Sewage and Combustion, which is nice. Second, the syngas IMEP is lower than that of methane due to the lower energy content of syngas, but it can be partly compensated, as you can see here with the dark blue point here, by a higher intake pressure, so boosted operation without knock occurrence. And for all investigated conditions, we get stable operation with a coefficient of variation for IMEP about 1%. The indicated efficiency that you can see with the empty symbols on the same figure is a bit lower for syngas, from 2 to 4%. But this difference can be partly explained by different combustion duration. So we can see here the bars that are higher for syngas than for methane, meaning that the syngas has a slower combustion due to its slower flame speed. When looking at the exhaust emission, we can see from the blue bars here that the unburned hydrocarbon are lower for syngas. The CO is lower as well, and the most striking point is the NOx, because we have almost a zero NOx emission, since we cannot see any orange bar for the syngas here. Last, the CO2 for syngas is a bit higher than that of methane because of the CO2 content in the syngas at the intake. So once this comparison is done, we can now switch to the addition of ammonia and first have a look at the input. So adding ammonia to the mixture will increase the stoichiometric air-fuel ratio, as you can see from the table here. The energy content will increase also because the lower heating value will increase. So we will have a more important energy input for the engine. And what is interesting is to look at the ammonia energy share, because only 15% of ammonia in volume in the fuel, for example, will lead to more than 50% in energy. So knowing this, let's have a look at the engine performance then. So we first look at the IMEP as before, and we can see that it will increase as function of the ammonia content in the fuel, mainly because of the higher LHV and the higher energy input. To keep this best IMEP, this best performance, we had to advance the spark timing here because of a slower combustion. And again, we can say that we get stable operation for all investigated condition with a COV-IMEP below 4%. Looking at the indicated efficiency, we can see a slight decrease with the ammonia content, as you can see here, and it is mainly explained by the lower combustion efficiency and the slower combustion, as you can see here from this graph. So we can see that the bar are bigger when adding ammonia, and it is especially true for the first phase of the combustion, the gray part here, because the flame speed of the mixture decreases when adding ammonia, and this has been verified with 0D kinetic simulation. The laminar flame speed here is driving the fundamental properties, driving the process. To finish, I will show you the exhaust emission. So we can see that when adding ammonia, the CO decreases in blue here, the same for the CO2. The unburned hydrocarbon are quite constant. And again, the most striking point is the NOx, because when adding only 2.5% of ammonia in the fuel, will lead to 2000 ppm of NOx at the exhaust. And those NOx are issued from the ammonia molecule itself. It is called the fuel rod. It is not thermal NOx as usual. When adding more ammonia to the fuel, we can see a stabilization of the NOx that can be possibly explained by the combustion efficiency, as we will see. It has to be said that the analyzer was not able to measure N2O in that case, and it is one of the most critical species when dealing with ammonia combustion. For the combustion efficiency, we can see that it is constant when we calculated it based on the HC and CO emission. But when we calculate it on the O2 content at the exhaust, we can see a decrease as function of the ammonia content, which means that the unburned ammonia are increasing. This can explain the stabilization of NOx we saw, because adding more ammonia will not specially lead to more ammonia reacting into NOx. And this can also explain the decrease of the indicated efficiency we saw earlier. Last, we can see that when increasing the intake pressure of the engine, so from the empty symbol to the filled symbol, here we can improve the combustion process, which can be nice. So to conclude, we studied ammonia enriched syngas, representative of sewage sludge in spark ignition engine. In comparison to methane, we saw that the pure syngas allows operation as stable as methane. We get lower performance with syngas, but this can be partly compensated with boosted operation, and without NOx. And also the emissions are reduced when using syngas compared to methane, especially regarding the NOx emission. When adding ammonia, we saw a higher performance, higher IMEP, especially by tuning the SIT due to an increase in the energy input. We saw also a decrease of the indicated efficiency because of potential lower combustion efficiency and slower combustion. The carbon emissions decreases due to the lower carbon content at the intake, but we increase the ammonia and NOx emission, and this will require catalytic exhaust after treatment, which seems possible considering the exhaust temperature we measured on the test bench. For possible future work, we would like to assess the unburned ammonia and the N2O at the exhaust, especially because the N2O has a global warming potential 300 times that of CO2, so very important. We would like to measure experimentally the fundamental properties of those blends, so the fundamental laminar flame speed, and why not investigating other syngas compositions, so manure-like or from municipal solid waste. That's all for me. Thank you for your attention. I would be happy to collaborate on any related topic about biomass combustion. And if you have any question, I would be happy to answer it. Thank you.